All right, so for our heat and power project, we wanted to investigate something that we thought was an interesting problem, and maybe we had a theory for a solution for it. So a current issue right now in cities is the urban heat island effect, where the heat capacity of concrete causes thermal energy to stick around after sunset, and also results in the cities and the concrete structures remaining hotter and building up thermal energy over the course of the summer. That energy gets convected to the atmosphere and environment around buildings, which is the city, and it warms up the temperature of the city. So we had an idea. So this is a basic setup of something known as an urban street canyon. You have a building, then a street, then a building. Picture yourself looking down the street this way. This is a building here, this is a building here. So this is how they are typically set up, right? You have a street flanked by two buildings. It could be any height, but you could have a row of buildings, say 100 feet tall is pretty normal. You see buildings like that frequently. And after learning about radiation, we realized that because all things emit radiation at any temperature above absolute zero, which these buildings are, I hope, we have radiation that is emitted. Some of it can go to space, and then it leaves. But some of it gets radiated right back to the other building, and then back to the other building. That radiation can't leave. So that energy sticks around until it's convected to the air. So we were wondering, what if we could get rid of some of that radiation by angling the walls? Now the radiation can leave, bounce, maybe, and eventually leave the area and go to space, like any radiation emitting from the roof. So this was the question. We weren't sure how to answer it, but we started reading into chapter 12 on radiation and decided to figure out how we could model this and see if we could answer this question.
So one of the things that we ran into while changing the angle of our walls, of our street canyon, was increasing what we call view factor. Well, what is view factor? Let me draw something on the board here for you. Imagine you're walking down a hallway and you cross the doorway of a room, or just glance across. Draw a room, unknown size, unknown dimensions. How much of the room are you going to see whenever you walk down this hallway? Well, you may say you'll see this much in this area. You may see even more. This unknown percentage of the room that you'll see can be solved with a simple equation created by a man by the last name of Hotel in the 1950s. And he uses what is called the cross strings method. Using this equation, Fi2j equals the sum of all crossed strings minus the sum of all uncrossed strings divided by 2 times string on surface I. Now this I to j is directional. It matters what we want to know. So we'll take, for example, just a straight wall or just a line. 2 surfaces that see each other. Then we will go and add some imaginary strings that have length related to these 2 that come across here. These are your crossed strings. These are your uncrossed strings. And then there is a string along the surface that you denote as I. Well, that surface is the surface that I sees J or I sees J.
Alrighty, let's see now how the cross strings method applies to our 2 different street canyons. So what we're going to be doing now is we're going to be calling the top of the street canyon space. So we'll draw a little dashed line there to represent space, and same on the straight wall street canyon. And so what we're going to do is we're going to use the cross strings method to see how much the street sees space and see how much each wall sees space. So we're going to call these walls a couple different things. We're going to call the right wall on both I. We're going to call the left wall on both J. And we're going to call the street on both K. Let's draw a couple of imaginary crossed strings in here now. So we're going to go from that top right to bottom left, top left to bottom right. And we're going to call these C1 and C2. Both of these are equal, and on the straight wall, they're 19.21 inches. Let's do the same for, oh, that curved a little bit. These are imaginary strings, so you'll have to imagine that it's straight. So we got C1 and C2, and on the angled wall street canyon, these are equal to 20.06 inches. For this analysis, we're assuming too that the tops of the street canyons, that 100% of that is seeing space. So we won't calculate those. Okay, let's see now what percent of K's field of view is space for the straight walled canyon. So taking our equation there, we're going to sum the crossed strings, which are C1 and C2. We're going to subtract the uncrossed strings. So in this case, it's going to be J and I. So J plus I. And then we're going to divide it all by 2 times the length of K. Okay? And this is going to give us the view factor from K to space. So when we plug in our numbers, we have C1 and C2 are both 19.21 inches. J and I are both 15 inches. And then divide it by 2 times K, which is 12 inches. And all of the inches go away. And when you do this, the math works out so that the view factor from K to space is 0.35 or 35%. So 35% of K's field of view will be space. Now let's do the same calculation, but this time let's do it for the angled wall street canyon. I'm also going to make a little note right here. We're going to put 35%. And when you do the math, you get that the view factor from K to space of the angled wall street canyon is 0.42 or 42%. So 42% of K's field of view for the angled wall street canyon is space. So now let's calculate the view factor from one of the walls to space. In order to do this, we have to kind of change our equation just a little bit. So if you consider the example we had originally of 2 plates parallel to one another with these 2 uncrossed strings and these 2 cross strings, well, that doesn't exactly work for the wall in space. So what we have to do is we essentially take this surface and we start to rotate it up and around here. As you do that, you can see that the 2 crossed strings start approaching J in space. And once this reaches 0, then the crossed strings will equal J and space. And our uncrossed string becomes C2, and our other uncrossed string just becomes 0. So plugging in numbers, we have our cross strings now are J in space, J plus space, minus our uncrossed strings, which is now C2, and our other cross string is 0, so plus 0, all divided by 2J. And this will give us the view factor from J to space. Plugging in the numbers, on the straight wall, J is 15 inches, space is 12 inches. Our C2 is 19.21 inches. And then plus 0, so it stays 19.21. And then divided by 2 times J, which is 15 inches. When you do the math, you get that this is equal to 0.26, or 26%. So 26% of J's field of view will be space for the straight-walled street canyon. Let's do the same, and also, due to the fact that they have the same geometry, this will also be the same view factor for I. So I also equals 26%. Let's do the same thing now for the angled wall street canyon. And when you do the math, you get that this is equal to 0.32 or 32%. So the percent of J and I's field of view to space for the angled wall street canyon is 32%. So you can definitely see that overall there is an increase in the view factor for both the walls and the street to space from the straight walled to the angled wall street canyon.
Okay, so now we have our view factors for our scaled down urban street canyon models. Now I want to take those and turn them into a useful metric that we can look at and analyze. So now that we have that, we can take our surface areas from our drawings of our models that we intend to make out of concrete from SolidWorks, and we can get surface areas for each of these surfaces. Since we are just looking down the length of our street canyon here, these all have a third dimension to them, and now we're going to introduce that. So for our surface areas, we have these here. Our K, or street surface area, for a vertical wall is 3 square feet. Our walls is 7.5 square feet, and top of walls is 1.5 square feet, which is this section just right here. Now, I went ahead and figured out what percent of the total area each of these areas are. So our street area makes up 25% of the total area, our wall area makes up 62.5% of the total area, and our top of wall area is 12.5% of the total area. It's the same deal over here, except with different numbers, because slightly different geometry. So 3 square feet for the street, 7.52 square feet for the walls, 0.84 square feet for the top of walls, and a different total area. And that gives us a street area of 26.4%, a wall area of 66.2%, and a top of wall area of 7.4%. This is just the percent of the total area. That's why our street area is different between the two, because there's a different total area. Now, to make this useful, we can take these areas here and we can multiply them by their respective view factor percentage. When we do that, that will give us what percent of the surface area actually sees space. So for our street, that would be our 0.35%, our walls would be 0.26%, and then the tops of the walls we decided to treat specially. Since we didn't solve for a view factor for the top of them, we assumed that this will be a view factor of 1. That's because we're making a reasonable assumption that this is the tallest building in the near area, so anything in its field of view would have to be the atmosphere, and therefore what we are considering to be a chance to go to space. So we're using a view factor of 1 for this. So we're multiplying that by 1, and then when we multiply all that, we can get our total percent. If we multiply these and then add them together, we have the total percent of our overall surface area that has a chance to emit to space. And that number came out for our vertical wall as 37.5%. Then we did the same for our angled wall, and that's our street percentage multiplied by our view factor from the street, 0.42, our wall, 0.32, and our tops of walls, which is once again considered to be 1. For that, we got a total percent emitting to 39.5%. So now we have a tangible thing to look at and compare the two view factors. Yes, the angled wall has a slight percentage advantage of surfaces that can see space. However, after thinking about this, we realized that that could either have a positive effect and a negative effect. One positive effect is that now, at nighttime, there's more area that can emit to space without any reflection at all, just how it works. But the downside is this means that there is more radiation incident on the surfaces during the daytime. So although this might mean it can cool off faster at night, it might also mean that it can warm up quicker during the day. Now we are hoping that the effects of reflection can counteract this during the day and make up for this disadvantage during the day, and then we can take advantage of this property at night. But that's what we will come to find out.
Okay, so we have our angled wall form here and our straight wall form here. Basically what we got going on is we have our sensor wiring harness here. We're gonna have 2 sensors in this wall, 2 sensors in this wall, and then 1 sensor on kind of the straight there. And that's the same for both of the forms. We've got some tape and stuff here, so hopefully they won't move when we pour concrete. And then we have these 2 threaded rods that are going to act like rebar. Once we put the inserts in, we're going to tighten those down so it kind of pre-tensions or pre-compresses the concrete a little bit. We've got these inserts here made out of metal. These are going to help us form the shape of our walls. And we've got these flaps here so we can pour concrete through them and get all that in there. So the forms have casters on them. So that way, after we pour the concrete, we can just pull the forms off and leave the bottoms on so we can roll them around for testing.
Finally doing the experiment. We've got our 2 pieces of concrete to simulate our 2 scale models of urban street canyons. One with a 5-degree wall, one with our straight wall. Right now we are hitting them with radiation with 4 halogen lights. Each one's 600 watts, and each street canyon is getting hit by 2 halogen lights. We're going to go through a warm-up process. We're going to simulate a scale day, I suppose, best we can. So we're doing this at night so we don't have other interference from the solar radiation, because it's hard to control right now with clouds and it being winter time. So we decided to make our own scale day at night. So the solar time we're having with the lights on is going to be 3 hours, and then we're going to have a 3-hour cool down phase. So we're going to run through a test like this. We've got both Arduinos hooked up to our sensors and our concrete, measuring our temperature at the walls, and we're going to log that over time. We're taking a data point every 15 seconds over the course of the 6-hour test. So this is the setup, and we're going for it.
All right, so to give you a little bit of information on the crete that we got,
So we took both of our forms. We got a orbital sander that you would use on like painting or paint on a car, and we used that to vibrate our forms. That way we could get most of the bubbles out. As you can see, there was some air trapped underneath the metal inserts in both the forms, a little bit more pronounced on the straight walled structure because we did not really know what we were doing with the concrete, and we made our concrete a little bit wetter. The angled wall was our second one that we did. We knew what we were doing. So
Okay, so as far as analyzing our results, we wanted to have a way to quantify which one will be better. So the best thing we could come up with is to analyze energy. So in this system, we can take our scale concrete models as this box. Assume this is the scale model here. We have our Q energy coming into our box, which is coming from the lights. So we do know this quantity here. It's whatever our Q dot, our energy flow rate is, times the amount of time that the light is on for. So we know that. That will go into here, and that will increase the temperature of our concrete. When we increase the temperature of our concrete, we know that internal energy is strictly a function of temperature with a constant mass. So, because of that, we know the internal energy of the concrete whenever we know the temperature of the concrete. Knowing the internal energy of the concrete will tell us how much energy will leave the concrete. So, coming out of our concrete, there's two ways the energy can leave. It can either be convected or it can be radiated. If it's convected, we know that's going to the outside atmosphere and it will increase the temperature of the surrounding air. If it's radiated, then it has a chance to go to space and not increase the temperature of the surrounding air. So the radiated heat transfer is more desirable. But how do we quantify whether or not we have more radiation or not? Well, because both of these models are about the same geometry, we can assume that the convection heat transfer is about the same for both. Because of that, we can make the association that if there is a change in the energy leaving the concrete, then it must be attributed to the radiation. So we can state that through some assumptions, but good assumptions, and some relations, that the change in internal energy of the concrete must be related to the change in radiation emitted from the concrete between the two, only comparing between the two. So we can state that delta U, which we know is equal to mass times heat capacity times change in temperature. This can also equal our change in Q out, which can equal our change in Q radiation. We'll put a squiggle there, roughly, because we can compare between the two, and we can assume that we have almost the same convection coefficients because both models were in the same area under similar conditions and are about the same geometry. So those are the assumptions we are making, and we are looking for change in Q radiation by looking at the difference in the mass times heat capacity times change in temperature. All right, so when we do our change in U calculation, we're going to factor in each of the masses of each piece of concrete. So we have two different masses, and therefore we'll have two different calculations, and we also will have different temperatures. The heat capacity will be the same for both, and their temperatures will be the change in temperature overall throughout the entire duration of the test. So throughout the duration of the test, if you look at one of our graphs, we were able to plot a trend line with all of our data points. Our R value of our trend line was pretty good. It was above 0.9, so we have good faith in it. If you look at the trend line, it increased throughout the test as energy was added to it from the lights, and then after the lights were turned off, then it went down. Now the test did end at a lower temperature than it started, and that's okay because it happened for both pieces. To determine which one lost the total amount of energy to radiation, whichever one lost more radiation, or Q out, overall, would have to be the winner here, since we decided any change in Q out was change in Q radiation. So looking at the two endpoints here, and the difference between the two, we can figure out the overall loss of energy.
All right, so as has been mentioned, if you look at our graphs, you can see that there's a clear ramp up section and a ramp down section from when the light is on to when the light is turned off. We decided that we wanted to take a look at the slope of this for the ramp up section of the solid wall and angled wall, and the ramp down section of the solid wall and angled wall, and compare the two to see which one's heating up faster and to see which one's cooling down faster. So when we do that in Excel, first of all, we have to divide the slope that Excel gives us by 1,440 to get our units of degrees Fahrenheit per minute. And then since our two concrete structures have different masses, we wanted to do this on a per unit mass basis. And since concrete buildings are extremely large, and because it gave us a little larger number that's easier to visualize, we decided to divide all of our slopes by tons so that we could have it in a per unit mass basis. So when you do that, for the straight wall ramp up, you get a slope of 0.36 degrees Fahrenheit per minute per ton. So basically, for our straight wall, when the lights are on, it is increasing by 0.36 degrees Fahrenheit every minute per every ton of concrete. For our angled wall ramp up, the slope was 0.50 degrees Fahrenheit per minute per ton. So as you can see, there's quite a bit of difference here. And as we talked about already with the view factors, this is not that surprising because the angled wall has a greater field of view of the sun than the straight wall does. So that's not very surprising. If we look at the solid wall ramp down, the slope is equal to negative 0.37 degrees Fahrenheit per minute per ton. So almost the same, just going the other direction as compared to the ramp up slope. Then if we look at the angled wall ramp down slope, we get a value of negative 0.50 degrees Fahrenheit per minute per ton. So the exact same almost as the ramp up. So once again, considering our view factors, this is also not very surprising, as once the lights are turned off, the angled wall surfaces have a greater view factor of the sky, and therefore have a greater chance of radiating heat to space. So we can see that reflected in this slope.
Okay, so now after taking a look at all of our data that we've gathered and applying this relation, we're able to come to the conclusion of the changes in radiated energy between the two pieces of concrete. Our value that we got for the angled wall would be our change in Q radiation was 0.88 BTUs per per pound mass. And our total change for, and this is for the angled wall. And then this one's for the straight wall. For our straight wall, we got a change of 0.83 BTUs per pound mass. We made sure to do it in per pound mass units because the mass is different between the two. We did get a slight improvement in change in overall radiation between the straight wall and the angled wall. It was slightly better for the angled wall. So although we may have only found that there was a 0.05 BTUs per pound's mass difference between the radiated heat, that has wider implications. Because even though that seems like a small number, and it is a small number, and there's not a guarantee that this result can be repeated, but it may be able to. If it can be repeated, and this is truly the difference, that is per pound's mass. When you scale this up, although it's a small number, it becomes a large one. A building is way more than a few pounds mass. It's a few thousand tons. So just a few thousand tons and this small 0.05 BTU per pound mass difference becomes a BTU difference. And then it becomes huge. And it might be worth investigating further because it might mean something.